This is Group 10 presenting our project cost optimization for the design and construction of a house with solar energy integration. Our system consists of three subsystems: energy storage, solar panel, and house design. Our objective function is to minimize the cost spent on energy, dollars per kilowatt hour, and materials used in a house in Los Angeles over 20 years, see total, utilizing a combination of solar and grid energy while meeting energy storage requirements. The system boundary is defined as the geographical area of where the house is being built. Within the boundary, the system includes solar panels installed on the roof, a battery storage system to store solar energy, and related electrical equipment. Environmental factors and external effects from neighbors are excluded for the system. Here's our system flow diagram representing the linkage between the three subsystems. We have independent inputs and outputs for the battery, the solar panel, and the house design. Our main coupled output is the linear sum of the cost of 1, building and maintaining an energy storage system; 2, electricity from the combination of solar panels and grid energy; 3, the entire building over 20 years. The shared variable between the energy storage and solar panel design subsystems is the battery capacity. Similarly, the energy storage and house design subsystems have the maximum energy as a shared constraint. Last, the peak monthly energy consumption is the shared constraint between the solar panel and house design subsystems. A system-level design is necessary because the solar panels, battery storage, and house design are independent, sharing critical variables that influence cost, energy efficiency, and long-term performance. Designing these subsystems in isolation would lead to suboptimal performance and potential conflicts in space, cost, and energy distribution.
So for the optimization model, here's the overview of the three subsystems and their corresponding parameters, design variables, and constraints. For the system level optimization, all the parameters were summarized in this slide with their corresponding description, symbol, value, and units. For the design variables, we have battery capacity, battery efficiency, battery area, and amount of energy drawn from the grid in each month as continuous variables, the number of solar panels for each model, the number of battery modules, and the number of windows on each side of the house as integer variables, the type of window and the type of insulation for the house as binary variables. The intermediate variables are mostly computed to represent the amount of energy generated in a certain amount or a certain year to satisfy some of the constraints. The objective function of the whole system is to minimize the cost spent on energy and material used in a house in Los Angeles over 20 years, which is consists of three parts: CE, the cost from energy storage; CP, the cost from solar panel; CH, the cost from house design.
So this slide outlines the full system constraints using our optimization model in instructional negative null form. Firstly, looking at the maximum energy constraint, the maximum area constraint. Ensure the battery system meets peak energy demand and the total battery area stays within the allowed limit. Looking at the roof area constraint, we ensure that the selected solar panels physically fit into our roof. The monthly energy demand constraint ensures the solar and grid energy combined are sufficient to power the house, and the battery capacity constraint ensures the battery can store the solar energy generated by the solar panels. Looking at the only one type of window, only one type of installation, as well as the minimum wall to window ratio, we ensure a realistic design for the house using these constraints. The side constraints enforce non-negativity for the solar panel counts and grid energy while applying logical limits for the window installation selections. And the domain of the design variables implement a domain for the design variables utilized. Considering the trade-offs, looking at the battery versus energy constraint, smaller batteries reduce cost, but may not satisfy the energy demand, which forces larger capacity of more modules to meet the constraint. Considering solar panel cost versus roof area, adding more or cheaper panels helps reduce the grid usage, but can violate the roof area limits. Considering grid energy uses versus battery storage constraint, drawing more energy from the grid can reduce reliance on battery storage, but increases the operational cost in the objective function. And construction costs versus energy efficiency requirements, using a cheaper windows and installation lowers the upfront cost, but may increase heating and cooling demands. Considering the system level model versus individual system models, unlike isolated subsystem models, the system model includes linking variables, which ties decisions across subsystems together. For our system model, we did not consider a coupled system analysis, and therefore we utilize all-in approach to model our system. which shows a coordinated system model rather than simply combining subsystem results. These coordinated decisions would likely be missed in an isolated optimization. Subsystem models individually minimize their own costs, while the system model integrates these into a single objective function. And modeling the system captures a global optimal solution and avoids suboptimal combinations that occur if the subsystems are designed in oscillation and then combined.
Mathematical modeling. So we're using an analytical modeling approach to formulate our optimization problem, and our goal is to minimize the total cost spent on energy and material used on the house by expressing all constraints and parameters in mathematical form. So for our major steps, each subsystem define their design variables to change to optimize the total cost. And for those design variables, we define constraints to ensure that the possible solutions were feasible and reasonable based on our research. And combining both design variables and constraints, we formulated a cost function for the energy storage, solar panel, and house design for a 20-year period. So we made a couple of assumptions for the energy storage subsystem. We assume that the batteries will not be replaced for 20 years, and the depth of discharge is constant and doesn't change over the 20-year period. For the solar design subsystem, we neglected high temperature degradation, weather conditions, and orientation effects on panel performance. And we also assume that no shading occurs. The annual degradation rate and grid prices are constant and do not change, and the roof geometry is approximated as a single bounding area. For the house design subsystem, the heating, cooling, and solar irradiation data are constant across each month, and heat gain and loss are realized through convection through walls and windows, solar gain, and gain from lighting and equipment. Lastly, no repairs or replacements for 20 years.
So for the optimization method, as we discussed earlier, we are working with an all-in-one combination of our subsystems when we modeled our system. So for our algorithm to produce results, we chose to do a tri-level optimization scheme, a diagram of which is shown here. The uppermost level of optimization is on the window and insulation type, and part of the cost function of this optimization problem is the optimal cost of the energy storage, solar panels, and electricity for the given window and insulation type. To find that optimal cost, we do another optimization on the energy storage system, where part of the cost function is the optimal cost of the solar panels and electricity for the given window, insulation, and energy storage variables. We find that optimal cost with one more optimization of the solar panel system. We chose to do this algorithm because we found it prevented some issues with the results getting stuck in local minima, and because this method allowed us to use the optimization algorithms that worked best for each subsystem as we had determined in our interim report. So for the solar panel system, that was Inland Prague. For the energy storage system, it was GA. And for the house design system, we were actually able to use the information we gained from the interim report about how the system works to optimize using a simple grid search over 9 possible combinations of design variables. Everything was implemented in MATLAB. And now for our optimization results. Here are the results. We present 6 runs, 3 with the same population size and crossover fraction, and 3 with different ones. We can see that in most of the runs, no energy will be extracted from the grid, which shows that the battery design and solar panel design sufficiently provide the house with the required energy. We find the optimal cost to be about $735,000 each time. When the hyperparameters change, we do see at one point we draw electricity from the grid and spend less on the battery and panels, but in this case, the total cost remains about the same as the other runs. This table is just giving a detailed breakout of the monthly grid usage, which was shown in the previous slide as the total E-grid.
Moving on to the post-optimality sensitivity analysis. For our only active inequality constraint, we obtained a sensitivity coefficient of 62.4 with an objective function value of $735,000. In other words, for every 1 unit increase in the constraint, the house cost changes by about $62,400. This makes sense because the constraint is active at the optimum, meaning it binds the solution tightly. For the parameter sensitivity, our system is most sensitive to CG, the grid electricity cost, with a parameter sensitivity coefficient of 55,703. A tiny change in cost per kilowatt hour from the grid leads to a huge swing in the total house cost. Next in sensitivity impact is the house length with the parameter sensitivity coefficient of 1,193. Last, the parameter sensitivity coefficient for the battery cost per kilowatt hour is 12.1, which means a $50 change in cost per kilowatt hour leads to an increase of only $1,210 to the total house cost.
Comparison of the optimization results show that the cost of independent optimization of subsystems add up to nearly $900,000, while all overall system level optimization reduce the total cost by about 20%. This shows that while individual optimization is optimal for each, but it ignores the coupling between subsystems, which can easily result in vast resource and lack of competitive. System optimization instead achieve lower cost and higher performance by coordinating shared variables and eventually allow for complete upgrade operation. In this project, all building materials and equipment with reference to the actual market price to ensure the realistic and reliable office simulation results. Although the simulated annual electricity consumption is slightly higher than the average published by the U.S. Energy Information Administration, this is due to the simplification of the calculation of cooling and the heating load and relative to traditional performance of building materials. The engineering significance of this project is shown at a high level of coupling between solar energy, batteries, and the building design, and to propose optimized framework for efficiency and low carbon home energy system. In future, it can be extended to multiply family and multiply area sanitary and take into account difference in user behavior, such as different air conditioning on times in summer, to make the system more relevant to help the development of sustainable building.